In the cosmic graveyard of dead stars, some refuse to rest in peace. These are the type Ia Supernovae, the undead stars that help us measure the universe itself. Meet the white dwarf, a stellar remnant about the size of Earth but with the mass of our Sun. These dense cosmic objects are what remain after average stars exhaust their fuel. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons. Their atoms are packed so tightly that quantum mechanics prevents further collapse. When a star like our Sun dies, it sheds its outer layers, leaving behind its core, a white dwarf. These stellar remnants are essentially dead, slowly cooling in space over billions of years. A newly formed white dwarf starts incredibly hot, but has no way to generate new heat. It will gradually cool and dim, like cosmic embers slowly fading in the night. But some white dwarfs refuse to fade away. In binary systems, they can steal material from their companion stars, slowly growing in mass. As a white dwarf gains mass, it approaches a critical threshold called the Chandrasekhar limit, about 1.4 times the mass of our Sun. When a white dwarf approaches this limit, its core becomes unstable. The stolen matter triggers runaway nuclear fusion, building to an inevitable catastrophe. These undead stars live on borrowed time. Once they cross the critical threshold, they detonate in one of the most powerful explosions in the universe, a type Ia supernova. In their final moments, these stellar zombies go out in a blaze of glory, briefly outshining entire galaxies and enriching space with heavy elements forged in their death throes. Let's explore the fascinating process of how dead stars can return to life through cosmic vampirism, a process that leads to some of the most powerful explosions in the universe. White dwarfs don't hunt alone. They need a companion star to feed on. When two stars orbit closely enough, the white dwarf's intense gravity begins to pull material from its partner. The stolen stellar material doesn't fall directly onto the white dwarf. Instead, it forms a swirling accretion disk, like water spiraling down a drain. As matter streams onto the white dwarf's surface, its temperature rises dramatically. The dead star begins to shine again, growing hotter and more massive with each stolen bit of stellar material. The white dwarf can only grow so large. As it approaches 1.4 solar masses, the Chandrasekhar limit, pressure builds in its core to catastrophic levels. Inside the white dwarf, carbon and oxygen nuclei are packed incredibly tight. The core becomes a nuclear powder keg, ready to detonate once it reaches critical mass. This vampiric process isn't quick. It can take millions of years of steady accretion before the white dwarf approaches its fatal limit. Astronomers have observed many such binary systems in different stages of this process, allowing us to piece together the full life cycle of these stellar vampires. As the white dwarf nears its limit, its core temperature soars to billions of degrees. Nuclear fusion becomes inevitable, leading to a runaway reaction. When the white dwarf reaches that critical 1.4 solar mass point, the stage is set for one of the most predictable and powerful explosions in the cosmos, a type Ia supernova. Now let's witness the most spectacular explosion in the cosmos, the type Ia supernova. But before we continue, if you're enjoying this cosmic journey, hit subscribe to join our space exploration. As our white dwarf approaches 1.4 solar masses, the Chandrasekhar limit, its core becomes incredibly dense and hot, reaching temperatures of over 100 million degrees Celsius. At this critical point, carbon fusion suddenly ignites in the core. Unlike a match lighting slowly, this fusion spreads through the entire star in mere seconds. The fusion wave, called a deflagration, races through the star at about 3% the speed of light, converting carbon and oxygen into heavier elements almost instantaneously. Within seconds, temperatures soar to billions of degrees. The immense pressure and heat trigger a runaway reaction that cannot be stopped. The star has reached the point of no return. The entire star detonates in a titanic explosion, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. In this cosmic forge, lighter elements transform into heavier ones. Iron, nickel, cobalt, and even precious metals like gold and platinum are created in the intense conditions. The explosion scatters these newly forged elements across space, enriching the cosmic neighborhood with the building blocks needed for future stars, planets, and even life. What makes type Ia supernovae special is their consistency. They all reach nearly identical peak brightness, making them perfect cosmic distance markers. This remarkable uniformity allows astronomers to measure vast cosmic distances and revealed one of the greatest discoveries in modern astronomy. the accelerating expansion of the universe. Now we'll explore how type Ia supernovae act as cosmic forges, creating some of the most precious elements in the universe through a process called nucleosynthesis. In the extreme temperatures of a supernova explosion, atomic nuclei collide and fuse, building heavier and heavier elements in mere seconds. Type Ia supernovae are responsible for creating many heavy elements, including precious metals like gold and platinum that we prize on Earth. The intense pressure and heat create perfect conditions for rapid neutron capture, known as the R process, which builds heavy elements faster than they can decay. During nucleosynthesis, lighter elements rapidly absorb neutrons, transforming through various unstable isotopes before finally becoming stable gold atoms. Every piece of gold jewelry you own was forged in the death throes of ancient stars, scattered across space billions of years ago. Only the extreme conditions in supernovae, temperatures of billions of degrees and immense pressures, can forge these precious elements. The explosion spreads these newly formed elements into space, where they'll eventually become part of new star systems and planets. Many elements we rely on daily, from iron in our blood to gold in our electronics, came from these cosmic explosions. In just a few spectacular seconds, these stellar zombies create and scatter the building blocks that will enrich future generations of stars and planets. As we conclude our journey, let's explore how these stellar zombies serve as the ultimate cosmic measuring tools, revolutionizing our understanding of the universe's expansion. Type Ia supernovae shine with remarkably consistent brightness, making them perfect cosmic distance markers, like standardized light bulbs scattered throughout space. By comparing how bright these supernovae appear versus how bright we know they should be, astronomers can calculate precise cosmic distances. This technique works because type Ia supernovae always explode with nearly identical energy outputs, making them reliable standard candles for measuring cosmic distances. In 1998, these cosmic rulers led to a Nobel Prize-winning discovery. The universe isn't just expanding, its acceleration is speeding up, driven by mysterious dark energy. By measuring thousands of these explosions at different distances, astronomers continue mapping the universe's expansion history with unprecedented precision. These stellar zombies revealed that dark energy makes up about 68% of our universe, fundamentally changing our cosmic understanding. Today, automated surveys scan the sky nightly, discovering new type Ia supernovae and helping refine our measurements of cosmic expansion. From stellar zombies to cosmic rulers, type Ia supernovae continue illuminating our understanding of the universe's past, present, and future. Thanks for exploring these fascinating cosmic undead with us. Like and subscribe for more videos about the universe's greatest mysteries and discoveries.